Imagine this. We might be the only intelligent beings in the universe. It sounds like something out of science fiction, but what if it's true? Have you ever wondered why we haven't found any signs of other civilizations yet? Maybe we're alone in the universe, or perhaps intelligent life is so rare that even within our galaxy we might be the only ones. Some might argue pointing to the thousands of galaxies out there. But is there really a reason for pessimism? The fact remains, we haven't discovered any other intelligent life. Of course, that doesn't mean it doesn't exist. It's possible that other civilizations are so rare that we simply can't see them due to the vast distances between us. Some scientists even suggest that there might be just one civilization for every 1,000 galaxies. That might seem strange considering that a single galaxy can have 1 trillion planets. So where did this estimate come from? A new study published in Scientific Reports offers one possible explanation for the Fermi paradox, which asks, if the universe is so big, why don't we see other civilizations? Perhaps life is so complex in its origin and development that it only arises under very rare conditions. The new study focuses on one specific factor, plate tectonics. The scientists even suggest updating the Drake equation, which estimates the number of potential intelligent civilizations in our galaxy, by adding parameters related to plate tectonics. The Drake equation has been around for decades and provides widely varying estimates, ranging from hundreds to millions of civilizations. The main issue is that we know very little about many of the variables in this equation. Of course, with the discovery of thousands of exoplanets, our knowledge is growing, but it's still very difficult to estimate the likelihood of life starting and intelligent species emerging on a planet. We know that one of the key conditions for life is the presence of liquid water, but it turns out that even this isn't all that rare. Our solar system has many bodies with subsurface oceans, or even entire oceanic planets. However, it's important not just to find water, but to find a planet where part of the surface creates land masses. On Earth, life originated in water about 3.8 billion years ago, but multicellular organisms appeared only 500 to 600 million years ago. What changed 539 million years ago that suddenly triggered such a burst of life diversity? Perhaps this is the key to understanding why we haven't found other civilizations yet. Scientists have proposed various reasons why life on Earth became more complex, and one of them is the onset of plate tectonics. Modern plate tectonics began in the Neoproterozoic era about 1 billion years ago and culminated 539 million years ago, coinciding with the emergence of complex life forms. Before this period, Earth's lithosphere was a solid shell rather than multiple moving plates like we have now. Plate tectonics might play a crucial role in the development of life. The plates constantly renew Earth's crust, bringing essential materials to the surface, increasing oxygen levels in the atmosphere and oceans, and affecting the climate. These environmental changes might have forced organisms to adapt and evolve, or else they didn't survive. Before plate tectonics started, simple organisms could have stagnated for billions of years. But why did plate tectonics start so late? It's likely that the planet had cooled enough for this to happen. It's worth noting that we don't see plate tectonics on other planets in the solar system. This suggests that plate tectonics, similar to Earth's, might be a very rare phenomenon. The authors of the new paper even propose adding 2 new parameters to the Drake equation: the number of planets with oceans and continents, and the fraction of planets with long-term plate tectonics. They estimate that about 17% of planets could have plate tectonics, while planets with oceans and continents could range from just 0.1% to 1%. By plugging these values into the Drake equation along with other variables, the most pessimistic scenario gives us a result of one intelligent civilization per 10,000 galaxies. Even with more optimistic assumptions, the result is still significantly lower than previously estimated. Where it was once thought that a single galaxy could host dozens of civilizations, now the estimate is 1 per 10,000 galaxies. This addition of parameters that consider plate tectonics, oceans, and continents might partly explain the Fermi paradox. It's no wonder we don't see anyone else if intelligent life is so rare. And these are just a few additional factors. How many more might we be overlooking? For those hoping to meet extraterrestrials, this doesn't sound very optimistic. But it's important to remember that the Drake equation isn't a precise prediction, but rather an intellectual exercise. Even if intelligent life is truly rare, that doesn't mean it doesn't exist. If we find microbes on Mars, Europa, or Enceladus, it will already change our perspective on life in the universe. As for space news, lunar exploration continues to gain momentum. Planned orbital stations, the return of humans to the moon, and even the possibility of a permanent human presence on its surface require the creation of standardized lunar time. Precise time measurement is crucial for the operation of satellites, landings, dockings, and other activities on the moon. But as our friend Einstein taught us, time doesn't flow the same everywhere. According to general relativity, gravity slows down time. The closer an object is to a source of gravity, the slower time flows for it. Specialists from the Jet Propulsion Laboratory have calculated that time on the moon moves faster by 57.5 microseconds per day. So if you imagine twins separated at birth, with one sent to the moon after 100 years on Earth, one twin would be just over 2 seconds older than the other. If a spacewalk can last several hours, how do astronauts handle natural needs? A high-tech diaper might be a solution, but it's not the most comfortable or economical option, considering that urine on the station is recycled back into drinking water. An idea inspired by science fiction arose, to create an analog of the still suit from Dune that would recycle sweat and other excretions back into drinking water. Such a system might be used by future astronauts on the moon and even on Mars. Meanwhile, the Europa Clipper spacecraft has encountered problems. Despite being ready for launch in October, some transistors in its electronics might not withstand the radiation near Jupiter. This was discovered at a late stage, causing a serious issue. Specialists are now searching for a solution to extend the life of these transistors, but a launch delay is also possible. Finally, there's news about dark comets that may exist near Earth. These objects could represent a new type of celestial body that hasn't been recognized before. If you ask people what objects exist in the solar system besides planets and moons, most will mention asteroids and comets. But considering the vast number of small bodies in the solar system and their different orbits and conditions, 2 categories might not be enough to describe them all. Dark comets could be another such category. Both asteroids and comets can approach the Sun due to certain effects that influence their orbits. The orbits of some comets are highly elongated. At their distant points, they can be very far away, but at their closest points, they approach the Sun so closely that they begin to form a coma and tails. Another characteristic feature is non-gravitational acceleration. For example, if we know certain parameters, we can expect an object to move along its orbit at a certain speed and acceleration. But sometimes it turns out that the object's motion differs from what's expected if we only consider gravitational acceleration. This additional acceleration makes it seem as if the object has engines, and they've been turned on. Some of you might remember that this was a key argument in the strange story of the first detected interstellar object, Oumuamua. It, too, exhibited unexpected non-gravitational acceleration, leading to speculations that it might not be just a space rock, but an alien probe or, at the very least, a fragment with a solar sail. However, this additional acceleration is often observed in comets. When a comet approaches the Sun, degassing, i.e., the release of gas and dust, actually acts like natural rocket engines, giving the comet additional acceleration. In the case of Oumuamua, the strange thing was that no obvious cometary outgassing was observed, leading to extraordinary theories, such as the possibility of alien technology. But besides outgassing, non-gravitational acceleration can be caused by other factors as well. For example, sunlight pressure can have a weak effect similar to a solar sail. There's also the Yarkovsky effect, where one side of an asteroid heats up under the Sun, and when it rotates into shadow, the accumulated heat is radiated away, giving the object additional thrust. This effect might explain why some asteroids, originally on orbits near Jupiter, gradually change their orbits and end up in near-Earth space. This is how potentially hazardous asteroids can appear. There are also other categories of objects being recognized now, such as active asteroids. These are objects with asteroid-like orbits but exhibit some comet-like activity. In the asteroid belt, there are objects that have a coma, like comets. The activity might arise from the sublimation of ice or due to instability from rapid rotation or collisions with other bodies. Inactive comets, on the other hand, are objects on comet-like orbits, but without noticeable activity. These could be nuclei that have lost most of their volatile substances. Orbits and distances from the Sun are important because they affect the composition and properties of these objects. Closer to the Sun, there should be less ice in bodies, while beyond the snow line, ice can make up a significant portion of the object's mass, leading to cometary activity. In 2023, another type of object began to be discussed: dark comets. These are described as a type of active asteroid that doesn't resemble known representatives of this category. These are near-Earth objects that don't exhibit a coma or noticeable outgassing, hence the term dark. But they demonstrate non-gravitational acceleration that can't be explained the same way as with other asteroids. Several such objects are known, most of which are small, 10 to 100 meters in size. They rotate rapidly and accelerate in unexpected directions, making them a subject of interest for scientists. The fact that these objects are in near-Earth space indicates the existence of a source that continuously replenishes this area with such objects. Why? Because the region around Earth's orbit is considered dynamically unstable for small objects. They don't stay there long, about 10 million years, before disintegrating, falling into the sun or onto other planets. The fact that such objects exist in near-Earth space now suggests they arrived relatively recently, and likely over the 4.6 billion years of the solar system's existence, new objects have repeatedly entered and exited this region. This means they must be regularly coming from somewhere. Another important fact is their unusual acceleration. It is likely related to the outgassing of water, specifically sublimated ice. These outgassings aren't powerful enough to create a noticeable coma like a comet's, but they still give the object some acceleration. The authors of a new study published in the journal Icarus conducted simulations to determine where these dark comets enter near-Earth space from. Most likely their source is the asteroid belt. Combining everything mentioned above leads to another interesting conclusion. If these objects contain or once contained ice and originate from the asteroid belt, this firstly suggests that there might be more water ice in the asteroid belt than previously thought, and secondly, that dark comets could be one of the sources of water on Earth. We still don't know exactly where Earth's water came from. There are different theories. It could have been asteroids, comets, or water that was on Earth almost from the time of its formation, or a combination of these versions. But now another possibility emerges. Icy objects from the asteroid belt may have fallen to Earth, delivering water. The authors of the article estimate that up to 60% of near-Earth objects could be dark comets, though the current sample size is very small. The high rotation speed of dark comets can be explained by the fact that these small objects may be fragments of larger bodies. Through sublimation and water vapor outgassing, the parent bodies spun faster and faster until the rotational effects broke them into smaller fragments, which continued to spin rapidly. In any case, we see that it is difficult to categorize all small bodies into just two categories, and perhaps with new discoveries, other categories will be added. Our solar system turns out to be more complex than we thought.